DuckDB under the hood, Module 11, the optimizer. Take a TPCH query that joins three tables, parts up, supplier, and nation. Disable the optimizer and run it. The query never finishes. Re-enable the optimizer and run the exact same CQL. 34 milliseconds. Same query text, same correct answer. Speed up of 640 times. In the last module, you saw how DuckDB executes a plan in pipelines. This module is about how DuckDB chooses which plan to execute. The optimizer is the component that turns the SQL you wrote into a plan that actually runs in reasonable time. DuckDB under the hood, Module 11, the optimizer. SQL is declarative. You write what you want, sum these rows, group by this column, join these tables, but you do not write how to compute it. The parser turns that text into an initial plan, and that initial plan is almost always slow. The parser produces what we call a canonical plan, cross products instead of joins. Filters sitting above the join instead of being applied early. Casts wrapped around every comparison. It is correct, but it is not what you want to execute. The optimizer takes that canonical plan and rewrites it into an equivalent plan that runs much faster. Equivalent means it returns the same answer for every possible input. Only the execution cost changes. Without this step, joins of 3 or more tables on TPC H-scale never finish. The optimizer is a pipeline of rewrites. DuckDB runs roughly 30 passes in a fixed order every time for every query. Fixed order means deterministic optimization time. You never get a query where the optimizer itself takes longer than the query. Watch the 4 most consequential passes. The expression rewriter folds constants and simplifies casts. Anything the engine can compute at compile time, it does. Filter pushdown moves where predicates as deep as possible, ideally into the table scan. Join order picks which table builds the hash table and which one probes it, using estimated row counts. Late materialization, when the query has order by plus limit, splits the scan into a narrow phase and a wide phase to avoid copying columns you do not need. Each pass takes microseconds. The whole optimizer typically runs in 1 to 2 milliseconds. By the end, the canonical tree has been transformed into a tight, efficient physical plan. 2 passes do most of the heavy lifting: filter pushdown and join order. Pushdown takes a where clause that the parser placed above the join and migrates it down toward the leaves of the plan, ideally into the table scan itself. Once a filter is part of the scan, only matching rows ever enter the rest of the plan. Fewer rows in means less work everywhere above. On a 60 million row line item table, pushing a single date filter into the scan is often the difference between seconds and minutes. Join order is the second big lever. When you write a query that joins 3 or more tables, the order you wrote them in is rarely the cheapest order to execute. The optimizer estimates the size of every intermediate result and picks the join order that keeps those intermediate sets small. Smaller table builds the hash table, larger table probes. That rule of thumb you might apply by hand is what the optimizer does automatically, and it considers all the orderings, not just the one you typed. 2 more rewrites that show up everywhere. Expression simplification touches every scalar expression in the tree. Multiply a column by 1, and the optimizer folds it away. No runtime multiply. Write column times 2 equals 10, and the optimizer rewrites it as column equals 5 and pushes it into the scan. Use like with a prefix pattern like AIR%, and the optimizer rewrites it as a range predicate. The scan can apply directly without invoking the like engine. None of this changes results. All of it removes work. Late materialization handles a specific shape. Order by plus a small limit. Without it, the engine reads every column you asked for, sorts the whole set, and returns the top 10. With it, the engine first scans only the column you sorted on, plus the row ID, finds the 10 matching row IDs, and only then fetches the wide rows by ID. For a query that returns 10 rows out of 15 million, this is the difference between reading 9 columns of every row and reading 1 column. Let us attach the TPCH scale factor 10 database, 60 million line item rows, 15 million orders. We set explain output to optimized only, then run explain on a join with 2 filters. Read the plan from the bottom. 2 table scans, line item on the left, orders on the right. Look at the filters listed inside each scan. Return flag equals R sits inside the line item scan. Order date after January 1995 sits inside the orders scan. The 2 scans feed a comparison join on L order key equals O order key. Because the filters already ran inside the scans, only the rows that survive flow into the join. Above the join, the aggregate counts the surviving pairs. A projection at the top exposes the count as column n. The thing to notice is what is missing. There is no separate filter node anywhere in the plan. The optimizer pushed both predicates inside the scans before any rows moved. Now turn the optimizer off and re-explain the same query. DuckDB will not rewrite anything. We get the canonical plan straight from the parser. Three things change once the optimizer is off. The two filters jump up out of the scans and land in a single filter node above the join. The casts on the literals, r cast as varchar, the date string cast as date, are still there in their long form. Every table scan is a plain sequential scan now, with no projections or filters attached. The parser produced this version. Both tables get fully read, joined together, and only then is the filter applied. The comparison join still runs because the equijoin condition is recognizable, but the input rows are no longer pre-trimmed. On scale factor 10, the work explodes. Re-enable the optimizer before doing anything else. Watch a single filter migrate through the plan. With every optimizer pass enabled, the filter is inside the scan. The line that reads filters L ship date bind date is inside the sequential scan box. The scan evaluates the predicate row by row as it reads from disk. Rows that fail the filter are dropped immediately before they reach any operator above. This is filter pushdown. The optimizer moved the where clause from a separate filter node into the scan itself, where it costs the least. With filter pushdown disabled, the scan returns every row of line item, all 60 million. The filter is not inside it. A separate filter node now sits above the scan. It receives every row and applies the predicate. Rows that fail are discarded here rather than at the source. Same answer, same data, but every row traveled through one extra operator before being discarded. On a 60 million row table with a highly selective filter, the cost difference is large. 3 expression rewrites, identity multiply, equation push, and like rewrite. Let me run all 3. Multiplying a column by 1. The plan does not show a multiply. The optimizer recognized that any number times 1 equals the number itself, an identity, and eliminated the operation entirely. The projection pulls p size out of the scan unchanged, 0 arithmetic at runtime. P size times 2 equals 10. The plan shows the filter p size equals 5 inside the scan, not a multiply. The optimizer saw that both 2 and 10 are constants, rearranged the equation algebraically to isolate p size, and pushed the result into the scan. No multiplication runs at query time, and the scan can skip rows where p size is not 5. Like with a prefix pattern, the optimizer recognized that AIR% means any string that starts with AIR and is lexicographically less than AIS. It rewrites the like to a range predicate the scan can apply directly. The like engine never runs. For a sequential scan with no index, this does not change the row count read, but it avoids per row rejects overhead. One more rewrite, late materialization. We ask for select star from orders ordered by order date, limit 10. 2 table scans in the plan and a join sitting between them on row ID. The bottom scan reads only the order date column. The narrow scan, just 1 column out of 9. Order by and the top n operator find the 10 smallest dates from that narrow stream. The other scan then uses those 10 row IDs to fetch the full 9 columns of orders, but only for those 10 rows. Without this rewrite, the engine would read every column for every row, sort 15 million rows by date, and discard all but 10. The optimizer produced this row-eyed plan automatically because it noticed order by plus limit on a wide projection. Your turn. Same join you saw in the walkthrough. Line item joined to orders. Filtered by return flag equals R and order date after January 1995. First, run explain with the optimizer enabled. Note where the 2 filters land in the plan. Then disable the optimizer and explain again. What changed in the plan tree? Finally predict, will the unoptimized plan still finish in reasonable time on scale factor 10? The exercise file walks through the full prediction. Re-enable the optimizer before running anything with explain analyze. Welcome back. Let us verify the prediction. We re-explain the exercise query with the optimizer enabled. Both filters end up inside their respective table scans. The line item scan applies return flag equals R. The orders scan applies order date greater than or equal to January 1995. The comparison join then receives only the matching rows from each side, pre-trimmed inputs instead of 2 full tables. With the optimizer disabled, both scans would read every row, and a separate filter node above the join would drop the non-matching ones afterward. On scale factor 10, that is 1 to 2 orders of magnitude more work. The plan still finishes either way, but the speed up from leaving the optimizer on is not subtle. Here is what we covered. The optimizer rewrites canonical plans into equivalent, faster plans. Same answer for every input, only the cost changes. Roughly 30 passes run in fixed order, deterministic, and fast, around 1 millisecond total for most queries. Filter pushdown is the workhorse. It moves, where predicates down toward the table scan so fewer rows enter the rest of the plan. Join order picks build and probe sides automatically using cardinality estimates. Expression simplification folds away constants, casts, and identity arithmetic. Late materialization splits wide order by plus limit queries into a narrow sort phase and a wide rowed fetch. You can disable individual passes with set disabled optimizers, which is invaluable when you want to see exactly what one pass is doing. Next up, Module 12, Real World Tuning.